Welcome to Fantastic Vision. Please subscribe us before you watch today's video. While the executives of ASML in the Netherlands are still worried about whether to continue exporting lithography machines to China, China's domestically produced LPD EUV lithography machines are completing the trial production of 7nm chips. This is not only a breakthrough in the semiconductor industry, but also a technological revolution that concerns the fate of the country. The birth of this machine marks that China has finally torn open the Iron Curtain that the West has laid in the field of cutting-edge chip manufacturing. Traditional EUV lithography machines require 13.5 nanometers of extreme ultraviolet light to carve circuits, and the technical difficulty is comparable to carving the Qingming Shanghe 2 on a strand of hair. ASML's EUV lithography machine costs $150 million and contains 100,000 parts. Only 3 countries in the world can produce core components. The LPD technology route chosen by China has taken a different approach, generating extreme ultraviolet light through laser-induced discharge plasma, which reduces energy consumption by 80% compared to ASML's laser bombardment of tin droplets, reduces the size of the equipment by 1/3, and reduces costs by 4/5. This strategy of reducing configuration without reducing efficiency has allowed China to build a 7nm lithography machine with 280 million yuan. Although it is temporarily unable to mass-produce 3nm chips, it is enough to meet 80% of industrial needs, such as new energy vehicles and IoT devices. This time, the LPD EUV lithography machine technology has made breakthroughs in 4 core technologies. The Harbin Institute of Technology team used high-voltage discharge evaporation of tin to replace traditional laser bombardment, reducing the light source power from 250 watts to 50 watts, but the stability has increased by 3 times, solving the problem of easy attenuation of extreme ultraviolet light. The silicon carbide lens developed by Changchun Institute of Optics and Fine Mechanics has a thermal expansion coefficient 90% lower than that of quartz glass, and the accuracy error is less than 0.1 nanometers after working continuously for 10 hours, which is equivalent to keeping a coin balanced on the top of Mount Everest. Quantum sensors calibrate the optical path in real time, and AI algorithms predict workshop temperature fluctuations, with an overlay accuracy of 3 nanometers, which is 20% higher than ASML equipment. The superlattice mask of the Chinese Academy of Sciences uses 2-dimensional material stacking to generate 0.1 nanometer level patterns, bypassing the molybdenum silicon multilayer film technology monopolized by the West. China's semiconductor industry is building a new ecosystem. Shanghai Microelectronics Complete Machines, the Chinese Academy of Sciences testing equipment, and North Huachuang's etching machines form an iron triangle, and the localization rate has jumped from 7% in 2018 to 42%. Zhuzhou Xinhua's 12-inch silicon wafer purity reached 11 nines. 99.999999999%. Nanjing University of Science and Technologies, RF photoresist passed the 5nm verification, and Japan's JSR's market share plummeted by 15% in 3 years. Even more subversive is SMIC's nano-imprint process, using 28nm equipment to produce 5nm chips, reducing energy consumption by 40%. This combination of backward equipment plus advanced technology made TSMC engineers say, "I don't understand it." ASML's financial report shows that in the first quarter of 2025, China's revenue share plummeted from 42% to 18%, and its market value evaporated by 32 billion euros. The Dutch government urgently approved the export of 1980 Di DUV lithography machines to China and set up a maintenance center in Shanghai to try to regain market share. The U.S. Department of Commerce quietly removed nanoimprint equipment from the entity list and tacitly allowed Applied Materials to cooperate with SMIC. Behind these changes, China's annual $450 billion chip import market is being restructured. When chip factories in Chengdu use domestic equipment to mass-produce smart car chips, and when the Quantum Computing Center in Lebanon tests the photonic chip architecture, the world finally realizes that the future rules of the semiconductor industry are being rewritten. This breakout battle proves that in the field of science and technology, the sharpest spears are often born when the hardest shields are forced to show up. And China is using the light of self-developed research and development to illuminate the end of the chip war. Looking back at history, from China's chips have no hope of catching up within 10 years, to Huawei will completely withdraw from the 5G market, the predictions of Western media have been falsified again and again. This catastrophe argument may prove to be a misjudgment again. Data shows that China's semiconductor equipment procurement has grown by 37% against the trend, and the 28 nanometers mature process capacity has accounted for 40% of the world. When Qualcomm's market value evaporated by $20 billion due to the loss of Huawei's orders, Chinese mobile phone manufacturers are using self-developed chips to seize the European market. Standing at the crossroads of history, the global chip industry is undergoing an unprecedented reconstruction. From the laboratory in Zhongjiang, Shanghai to the wafer factory in Dresden, Germany, from the lithography machine R&D center in Tokyo to the packaging and testing base in Singapore, scientific and technological workers are still struggling to break through the physical limits. As the chip pioneer Moore said, "There is no eternal leader, only innovators who never stop." The ultimate winner of this chip war will surely belong to those countries and companies that can stick to the spirit of openness and cooperation in the storm.